Okay, so we're very lucky today to have Dr. Hamid Hosseini and Dr. Adib Allahham, both of whom are colleagues of ours at Newcastle, working in the National Centre for Energy Systems Integration. And they're going to cover, I think, 4 different operational models that have been developed for CESI over the course of the time they've been working on the project. So they'll, as usual, they'll speak for 30 to 40 minutes, and then there'll be some time at the end for us to ask some questions. So without further ado, take it away, Hamid and Adib.
So good morning, everyone, and thank you very much, David and Matt, for inviting us to prepare to present our operational model 1. Basically, as David said, just to kind of clarify or add to what David said is, in National Center for Energy Systems Integration, this 5-year project, which we got some extension, we developed 2 operational models and 2 planning models by different partners, actually, of the university, of this center, of our center, actually. But this operational model 1 was the model that Adib and myself have developed together and have done a range of analysis and evaluations with this model. And then, me and Adib are going to present this model and see how it worked, where did it come from, and the instances of application of this model for some energy networks analysis. So the outline of the presentation today is about review of planning and operation of the integrated energy networks. So that's the abbreviation for IEN. And the techno-economic environmental evaluation framework for integrated gas, electricity, and distributing networks. And then instances of application, so around the 4 items, which again, we go in detail further. So, but in general, it's more about techno-economic environmental analysis of different kind of, configurations or scenarios for integrated energy networks. And then we are going to give a presentation about these coevolution cycles and what does this mean for integrated energy systems analysis, and then a summary of our presentation. So a review of planning operation of integrated energy networks. So Adib and myself have published a paper in Renewable and Sustainable Energy Reviews, and so we did a review of papers on operational analysis, optimal dispatch, and operational planning of integrated multi-vector energy networks. And so we selected papers that were at least on 2 vectors out of these: gas, electricity, district heating, and cooling, if there. And also networks or papers that were on network operational level analysis, but not just a hub level. And the papers, actually, we have considered the papers published in prestigious journals and conferences, and so we found, and almost recent papers, I think around 4 or 5 years ago. So we selected something around 190 papers. So this graph shows actually, where these papers are published. So basically 115 were published in prestigious prestigious journals, and 71 of them was from prestigious conferences, which majority of them coming from IEEE conferences. And this graph actually shows the breakdown of these journal papers, which you can see, the majority of them are coming from either IEEE transactional power systems, applied energy, IEEE transactional sustainable energy, and IEEE transactions on smart grid. Basically, you can see it's all about prestigious papers and journals, actually. And this actually which country has every of this paper is coming from, and based on the affiliation of the first author of the paper, and the center and the country of them. And then so you can see that 72 papers from China, and then 31 from UK, from US and Iran, and then the rest of the papers from other countries are less than 10 papers, actually. And then basically you can see that this analysis of integrated gas electricity networks and integrated energy networks is basically, worldwide and considered by all the countries, and it's a concern of almost all the countries, actually, if you can say it that way. So what do we mean by operational analysis? So this means that, we assess the operational condition of the networks, and if I can just move this, and, ensuring that the networks are meeting the demand without violating the operational limits. And optimal dispatch means, it's about optimal operational scheduling of integrated energy networks, which again, we normally consider for the next few hours or for the next day, but not further horizon than that. And this means that, in order to meet the demand with least operational costs as the operational objective function, then how much the amount and scheduling of the energy from different sources needs to be, and also about the coupling components. So how much they should work actually. And optimal planning is about investment planning of all the assets of integrated energy networks for a horizon of time, for example, next 20 years, next 50 years. And, in this for this analysis, we consider that, all the capital and operational costs of operation of operational cost of the networks all mapped to a base year. We should minimize that to make sure that the integrated energy networks are meeting the demand and current and future projected demand, with some subject to being operable and also optimally dispatchable actually at all the time steps. So what we did in this paper actually, so just about, for example, the operational analysis that we did. So basically, we just considered all the papers on operational analysis, and then we went through the key findings, and then we considered all the keywords of these key findings, and to see that, what's the idea of this paper, what they are speaking about. And based on that, we found, and also, the important thing was that, all these findings were around energy trilemma elements, so which are security, flexibility, and affordability. There are several other definitions for energy trilemma, but these three terms were actually more spoken or discussed in this paper. So we consider these three as the elements of energy trilemma. So yeah, we just summarize these the key findings of these papers around energy trilemma. And we found that, for example, in operational analysis, papers on operational analysis, the papers were all more discussed actually interdependencies or uncertainty and integrated operation of the integrated modeling of the networks, as well as renewable generation and storage, and the rest of the topics. So the same, for example, in optimal dispatch, the papers more discussed storage, then line pack, then power to gas, then renewable generation and coordinated scheduling, and less about congestion and rest, And the same for and then the same for the operational planning. So then papers were more on co-planning, networks, interactions, and stochastic planning of these networks. So we put the key findings of all these papers all together, and then this paper actually happened. So I'm not going to do the all to read around a few pages of written papers to you and just waste of time, but the details are there actually in the paper. And so based on all these findings of these papers, actually we identified some future research directions, which I think, if you like, do you like to explain this one?
Yes, Hamid, thank you. So just after reviewing all these papers, we discovered there is a main gap in this literature, or this must be covered, which is a smart energy management system of these integrated networks. So suppose that we have gas, electricity, and discrete heating network, and for sure we have the end user of the energy. So this energy, we suppose we need to manage these systems, not from the point of view only electric networks, only gas network, only heating networks, no, as an whole energy system. And we define somehow that there is a fundamental requirements to have all this equipment or all these participants in this energy networks or energy systems to be can be communicated, and also we need for sure we'll have a huge amount of data. So for sure we need somehow AI and machine learning to process and to inform the energy management system about what's going on. So next I have Hamid, yes, the next please. Yeah, so also we let's suppose that we have currently, if we have in electricity networks, so there is control room for this electricity network, and this this control room try to manage or control the network to solve any issue related to congestions, something like that, to if there is any uncertainty in the load, to meet the demand and everything, and to make the network operate technically. Also, for if there is also control room in the gas network, and also trying to solve any congestions and also to deal with this demand uncertainty. So suppose that we have two networks and they are geographically close. So and we need to will present letters how the integration is very beneficial for to provide service to deal with this problem like congestions and uncertainty of the load. So if we need to have one control room to control both network, and we have this coupling component, which for example in this figure we have electrolyzer to convert energy from electricity to hydrogen or to methane gas and inject it in the gas. So how these coupling components can be also controlled. So this is one of research gap that's to deal with that. And to be honest, this was very helpful for us, because based on this idea, with Dr. Sarah Walker, Damian, and Hamid, myself, and Zoya, and also in collaborations with Kiel University, Professor Zongvan, and also our colleagues, Dr. Mehdi from De Montfort University, decided to develop a proposal to develop control system for integrated gas, electricity, and heating networks, and basing on these ideas. And it's not only in this work, in this for sure in this proposal we didn't limit it us only a technical side, but we go further to discover business models for this control system, what we can provide as services to this network, because it's one of the gap in this paper as well, about the economic aspect of this integrated gas electricity networks. And hopefully the proposal will be submitted next week. Hopefully we can get the fund to continue the research in this interesting field.
Excellent. Thanks, Adib. Thanks. And also, we had future other research directions in the project, in the paper, that we just preferred not to present them because of the time limit, actually. So it's basically about uncertainties and also economics of energy systems integration. So now moving to basically what was the purpose of presenting this review paper? It was just to show that one of the works that Adib and myself have done, that's not a problem at all. But more important thing was that based on this review paper, actually we identified, and in parallel to our works, actually we identified some research gaps And based on these research gaps, then, we developed this techno-economic environmental evaluation framework that I'm going to present now. And then the instances of application that, from each of these instances, actually, we published the paper. So basically just wanted to let you know that, this review paper actually was just like a direction for us, or a light at the end of, very far, so that we know that in that direction we need to do some research, and these are the gaps that we need to address. So this techno-economic environmental evaluation framework for integrated gas, electricity, and distributing networks, we need to first define some terms. So first of all, what do we mean by technical parameter? So this technical parameters actually shows that, the amount of energy that's imported from upstream gas networks to the distribution level gas and electricity networks, integrated networks, sorry. And or for example, if you are speaking about transmission level, technical parameter of transmission level means that, amount of energy imported from either natural resources or from import to the country, basically the amount of energy imported from one upstream step to these level networks, actually. And basically, and for example, if the technical parameter is less or smaller, it means that, the energy supplied by the upstream networks or natural resources is smaller. So meaning that, for example, less amount of take up of energy from upstream or from natural resources. And, this actually enables us to have an idea of the security supply and self-sufficiency of distribution networks. Or same for economic parameters. So economic parameter for us means operational costs of integrated gas, electricity, and distributing networks, integrated energy networks, which is again about the cost of purchase of energy from upstream, and also the amount that this economic evaluation actually shows that, how different factors can lead to reduction of energy, reduction of cost of meeting the final energy. And the environmental parameter means that the amount of emitted CO2 equivalent as a result of final use of energy again supplied by the upstream networks. And also this environmental parameter actually shows, shows allows for quantification of impact of more utilization of energy storage devices or more renewable energy sources into the local networks and the impact of them on the carbon. So this is the block diagram of our framework. And so this techno-economic environmental evaluation framework has some inputs. So for example, the loads in different networks, the topology of the networks, the generation, if we have, for example, some renewable generation, or if there's if for any uncertainty analysis, if there's uncertainty parameters, or for storage devices, we have parameters there are also same for coupling components and also for economic and environmental evaluation parameters. So the unit factor of, or if there is any uncertainty associated. So this core of this framework has a technical simulation engine, which I'm going to present in the next slide. So basically, this TSE, technical simulation engine, performs a technical evaluation, and so considers, all the integrated, basically through a whole energy systems approach, considers that, if you have loads, generation, coupling components, different configurations of networks, and different anything, so what's the impact on the technical evaluation? And technical means amount of energy uptake from upstream. And then once this is done, then we go to the environmental and economic evaluation. And then once this is done, then we have a picture of the techno-economic environmental evaluation and of the whole energy networks. And so the whole energy networks, as well as just for gas, just for electricity, and just for the distributing networks. So what's this technical technical simulation engine? So for the gas network, so we consider the balance of gas flow in every node of the network, and also we consider so for the flow of the branches, we consider the pressures at two ends, and also the diameter or the length of this pipe, as well as the temperature of the gas, and also this friction factor, this relative density, and also this compressibility factor that we consider is about the mixture of the gas. So just wanted to let you know that in our model, actually, we consider the mixture of the gas. So basically, for example, if you have hydrogen, high amounts of hydrogen, very low amounts of hydrogen, or different components of the gas, for example, methane, ethane, butane, and all these things, or the nitrogen, or any kind of parameters, components that your gas mixture has, we can consider in this network, in this simulation. Same for electricity network. So balance of real and reactive powers or energy power flows actually at every bus of the network, and the same for the district heating network. So the balance of hot water flow and the waste of temperature in every pipe, and the mixture of these different water flows with different temperatures, and all that basically, So and also we have considered different coupling components. So for example, heat pumps or CHPs or power to gas, and also we have considered gas and electricity storage devices, and also the network models are soft linked, so it's unlike a unified Jacobian. And also the same for economic and environmental evaluation. So once we know the technical operation and the technical parameter of the network, then we just multiply these values for operational cost and carbon emissions of gas and electricity networks, and these are coming from Ofgem and government and parliament documents. Just because of the time, I think we need to a bit rush. Sorry. One of the instances of application of this network was about this framework. Sorry, was about. And basically, we have published this actually in IEEE ISCAS conference in 2018. Was that if we have transmission level gas and electricity networks and distribution level gas and electricity networks, and these are all coupled to each other at all the levels, and upstream and low stream, and the whole idea of these scenarios were to consider that if we have any problem or any event, if you like, in any level, just the gas network of distribution level, or just the electricity network of transmission level. So how this is actually this event or this problem, or if there's any constraint set by any network, then how this is kind of propagated in the whole energy system, and how this is transmitted and impacts actually the techno-economic environmental, and again how networks can support each other in case there's some problem somewhere. So that's the type of analysis that we did. And Adib, do you like to present this couple of slides?
Yes.
But very quickly, I think because of the time, we are in time shortage, I think.
Sure. So just Hamid mentioned that for the distribution at distribution level, we solved the model of integrated gas and electricity network in soft linked. We soft linked the gas and electricity networks, but at transmission level in these papers that Hamid mentions, we try to solve at transmission level using like these equality equations to calculate the gas and electricity flow at transmission level using unified solutions. And I mean by unified solutions, we have like applying Newton methods. We have the state variable. If you can see here, we have the state variable of electricity, of the gas network, and we developed like Jacobian matrix J. We unified Jacobian matrix for to solve the method. Next slide, please, Hamid. Yeah, if you can have a look on this, like the Jacobian matrix, you can see in this like corners, in the left upper corners, you can say F, which is the flow of the gas, H is the consumptions of the gas energy in the compressors, compression stations. P, it's or by, it's the pressures, and we have this. If you can see in the like low level, right, this is the component related to the electricity network. And in the middles, you can see here the components related to the coupling component. So for example, if we have power to gas, the first RTM in the column up, you can see first this one, yeah, you can see the change of flow as the results of operating the gas, power to gas. You can see also down in the fourth, this one, yeah, the change of the power injected or like absorbed from the power to gas, and the effect of power to gas on the power balance. The next item here is it's the as we have sometimes we have electric compressors. So what's the impact of these compressors on the power balance? And for sure, if you have also another component like gas-fired generators, I mean generations using powered by or supplied by the gas, so there is a need to add another column, and in these columns we can show the impact of generated power on the gas flow, and the impact of generated power on the power balance in the networks. Next slide, Hamid, please. Yeah, and in this paper as well, we apply this Jacobian matrix on standard networks to compare the results of this Jacobian matrix with the reference papers considering the same networks, and fortunately the results it's confirmed, and this Jacobian matrix helped us to solve these power gas and power flow equations using the Newton-Raphson and in one or in unified form, if you want. Thank you, Hamid.
Adib, thanks. So so as you know, Adib said, we also have published that work. Again, another instance of application. So it's about storage configuration in gas and electricity distribution networks. And we have published this in IGEPES. And it was about Findhorn networks. And if you have stored in single vector storage, for example, just in electricity network, or a vector coupling storage. So for example, if we have power to gas and then gas storage and injecting into the gas network. So what's the impact of these energy storage devices on the techno-economic environmental operation of these integrated networks? And also, if we have different sizes of storage, so if we have different sizes of gas storage, or this is for example for electricity storage, this is for gas storage, and so what's the impact on the techno-economic environmental evaluation? And also if we have, for example, some scenarios around high renewables or low renewables and things. So basically this is one of another instance of application of this framework. Another one was that if we have geothermal storage, and also we want to decarbonize the heat of, for example, for Findhorn networks. So how can this framework help?
I can interrupt you, please, for 1 point. So the main idea from the previous paper is about the vector coupling storage. This means usually there is storage in gas or electricity. In this paper, we introduce vector coupling storage. That's we take the energy from one vector and we storage in another vectors, and do some sensitivity analysis about the size of this storage, the impact on the TEE, and also considering different scenarios of renewable energy. Sorry for the interruptions.
Thanks, Adib. Thanks, please, always. Yeah. So we have, just again, because of time, I need to go a bit quickly, sorry about that. But we have considered two types of geothermal energy storage. So that's the work that we did with Charlotte Adams at the time that she's been a professor in Durham University. So high temperature geothermal energy storage and low temperature geothermal energy storage. So high temperature means that, you know, the temperature of the water taken from underground is enough to supply the district heating network, but in low temperature, it means that, you know, we need to put a heat pump basically here to boost the temperature of this water basically, and then feed it to the district heating network source. And so if we have this, so we have considered several configurations of networks, or if you like, several future scenarios for configuration of networks to meet or to decarbonize heat, having this geothermal energy storage. And so, for example, around 9, I think, scenarios. So, for example, all electric. So means that, you know, we have just a smart energy, smart electricity network, and we have electric heaters to meet the heat demand, or all gas. So gas network, gas boiler, and heat demand. Gas and electricity. So a combination of gas and electricity, and so from the gas side, it's gas boilers, but from the electric side, it's heat pumps. Basically, you know, whether we have low penetration of heat pump or high penetration of heat pumps. And then if we have high or low temperature, high temperature or low temperature geothermal energy sources, and, you know, these two actually feed the district heating network source, and this meets the heat demand, you know. And if we have CHP, so gas and electricity network coupled with the CHP, again, gas with gas boiler, CHP again with electric heater. And if we have low temperature gas geothermal, but with this electric heater, so in these configurations, actually electric heater were at district heating network source in case that, you know, the geothermal can't meet the demand. But in this one, if that electric heater is at the final load, and, you know, to meet the rest of the heat demand, if you like, and also if we have low temperature geothermal, and we use gas boilers from gas network to meet the rest of the heat demand. So several configurations. And, you know, once we performed techno-economic and environmental analysis of these scenarios, so we just found that, you know, most efficient, cost-effective, and least carbon-intensive configurations to meet the heat load were high-temperature geothermal energy sources with the electric heater at district heating network source, and then high penetration of heat pumps, and then low-temperature geothermal energy storage with electric heaters at, again, district heating network source. And then, you know, the rest of the scenarios or configurations were just ranked based on their performance. But these were actually, you know, the least PEE configurations. Another scenario with this work actually that we did, that, you know, if we have some increase in the wind and PV levels, then how these scenarios are kind of compared, and how does that actually impact the rank of this scenario. So I don't present the last one, but for example, if we have changes or increase in wind and PV levels, that, for example, we see that, you know, there is some decrease in TT parameters of the configurations relying on electricity network, but nothing on the gas network side. And then, you know, this paper was published in IET Smart Grid. And another instance of application was this uncertainty analysis of impact of in the networks integration level and storage. So if we have different levels of integration of networks and different storage devices, how does that impact the techno-economic environmental performance, provided have some uncertainties? And this work has been published in Energy Journal. And for example, we have considered the uncertainty of electricity and heat loads, uncertainty of wind and PV generation, and uncertainty of economic and environmental unit factors for evaluation. And also we have considered probability distribution function, and we sampled it through Monte Carlo simulation. And this is the configuration of the network. So for example, this is electricity network, gas network. If you have electricity storage, power to gas, gas storage, and CHP, and different configurations of whether networks are separated or just electric storage, or these network, these components actually. So one direction of energy conversion. So the same with storage devices, two direction of energy energy conversion between networks, and then is the same configuration with energy. So then, as I said, different integration levels and storage devices in this network, and also considering the base case, and if we have some improvement in technologies, and also if we have high renewables at low loads or low renewables at high loads, high heat and electricity loads. So this shows, just very quickly, this shows that, for example, if you have electricity storage, power to gas and gas storage, this has the lowest economic environmental parameters compared to the rest of the scenarios or configurations. And for example, this shows that, if you have some technology improvement, so improvement in the efficiency of coupling components, so for example, power to gas or CHP, and how does this impact the techno-economic environmental evaluation or performance of these networks? And the whole thing actually shows that if we have these efficiencies are increased, then this leads to lower techno-economic environmental parameters and more in actually the configurations with bi-direction of energy conversion compared to the single direction of energy conversion. And the whole idea, the key finding was that the efforts to improve efficiency of coupling components by equipment manufacturers are very important goals to pursuit of lower T parameters in future integrated networks. And also, if we have opposite direction of renewable generation, renewable and loads variation in gas and electricity networks with all these uncertainties, the whole idea actually shows that, the configurations with more integration of the networks have better T performance parameters compared to no integration, or just, for example, single integration of networks. And basically this shows that those configurations, so basically if we are going to go to the net zero 2050, and at that time we are having more renewable generation, and despite all the uncertainties in the networks, we need to go for more integrated operation of these energy networks. So Adib, co-evolution cycles and yourself, if you like.
So thank you, Hamid. So just the as case study in this paper, we consider it like the real world data collected from the Fendhorn village, and this is, I give in these pictures just a photo of this village to have an idea about the scale of this case study that we consider it in our simulation and in our analysis. So now, as you know, this next slide, please, Hamid. Yeah. As you know, this work is like within the framework of CESI projects, and within CESI project we have what we call co-evaluation cycle. So in our work, always in CESI we consider architecture, policy, supply, infrastructure, demand, and demonstrators, and we have three stages or three stages of co-evaluation. In the first one, so we need to establish the scenarios, establish the small case study, and learn from this case study and applying to try this future scenarios until 2030. And based on this knowledge that we get from this case study, we can apply and we can increase the size of this our studies. For example, in the first stage, we considered Fendhorn as case study, and then we look to upgrade our models and our case study to go for more regional level, and we consider it and this regional level the North of Tyne as case study. And also in this North of Tyne case study, we try to project the future energy scenario until 2040, and to study how what we need to update, how we can need to develop or enhance our models to answer these questions of future scenario 2040 and at regional level. For sure, we have like co-evaluation cycle 3, and in this case, maybe we are looking to move from regional level and to go at like national level, and like for the future scenario until 2050. So somehow, what we learned from like local level, like Fendhorn, we need to apply to regional level, and what we learn from regional level, we need to apply and go further to apply for national level. And for sure, at each stage we try to communicate with stakeholders to define the most appropriate research questions at each level for each stakeholder. So now, next slide, please, Hamid. So as part of co-evaluation cycle 2, we try to go for like bigger demonstrator, and we consider it like North of Tyne combined authority. Here I show here like the general network, if you want, of the gas and electricity network, and just to show how complicated this network is. And for this regional, this region is composed of 3 local authority: Newcastle upon Tyne, North Tyneside, and Northumberland. So it's like geography, it's a big area, and it's composed different type of consumers, residential, commercial, and industrials, and also huge gas and electricity networks that we can consider. And given that, next slide, please, Hamid. So in this case, so as we in Fendhorn as case study, we went with like gas and power flow, because we have like limited number of resources, so we don't it's not we don't need to know the dispatch optimal dispatching of each of resources and generator. But with this huge regional network, so we upgrade our model to consider gas and electricity optimal power flow, for sure, with the objective functions to minimize the cost including no gas electric generation, cost of electric generator supplied from another gas network, not from the local networks in North of Tyne, and cost of gas supply. And for sure, these networks is this model. In this model, there is a set of equality and inequality constraints expressing the balance of power flow, gas flow, and also some limits limited to the used resources in the both network. So next slide, please, Hamid. And also to like here also to trying to to answer more questions from the stakeholders at regional level. So we tried also to upgrade this what we call TE parameters: technical, environmental, and economic impact, to consider environmental not only the cost of CO2, no, so CO2 emissions and intensity, which is amount of CO2 emissions per energy supplied, the renewable energy integrations, and overall efficiency of the gas and of the integrated networks. Next slide, please, Hamid. And also we considered in the economic not only the cost of energy imported from upstream, no, also we consider the abatement cost of CO2. And for next slide, please, Hamid. And for the like technical parameters, we consider reliability, resilience, and flexibility. And in this like capacity, in reliability, we consider capacity margin, network capacity, as resilience, self-sufficiency, flexible capacity or headroom, and also rate of heat electrifications. And for sure, as we consider here somehow trying to reflect 2040 future scenario, energy scenario, we try to consider the impact of the penetrations in 2040 of heat pump and electric vehicles on the change of demands in these regions, and what the impact that's at the network operation of and these TE parameters. And this is like what the work that we developed for the case of case study north of that. Next slide, Hamid, and it's for you.
Yeah, so thanks, Adib. So just to summarize what we have done or what we presented is, a framework for techno-economic environmental performance evaluation of integrated gas, electricity distributing networks and all their possible coupling components and configurations with considered acts also were developed. The framework actually evaluates different storage configurations, different scenarios for decarbonized heat, different sources of uncertainty, also can evaluate impact of any networks configurations or any parameter on the techno-economic environmental performance of integrated networks. The framework has been applied to Findhorn and North of Tyne case studies. The framework provides through those coevolution cycles actually. And also the framework provides a base, and the whole idea is that the framework provides a basis for making a well-informed and risk-based decisions for future integrated energy systems. And also this framework has presented, has led to several publications in prestigious journals and conferences. So it has really helped for the academic impact of our center. So thank you very much for your attention and for your time. And if there is any questions, Adib and myself are more than happy to answer.
Okay, thanks very much, both of you. I think the standard thing is that we normally stop recording now so that the questions are kind of off the record. So I'll just stop that.